This video will illustrate the methodology required to perform a test of linear correlation on a bivariate set of data using formal hypothesis testing procedures. When we talk about correlation, we're typically talking about some kind of relationship that exists between a set of data for two variables. So a bivariate set of data has to be present, and we're trying to determine whether there is some kind of relationship. It could be a linear relationship, a quadratic relationship, an exponential relationship, a periodic relationship, sinusoidal relationship. The point is we're looking for some kind of relationship between the variables. And so where an engineering technologist would use this is when you do some measurements of two variables and you want to determine whether there's some kind of physical relationship or some kind of equation that relates the two. You can use this testing procedure to determine whether a significant relationship that is suspected actually exists. So if we start out with our set of variables, our two variables, x and y are measured simultaneously. And when you graph them on independent axis, usually the x-axis is the horizontal axis, y-axis is the vertical axis, you orient them perpendicular to each other, we end up with data ordered pairs, x comma y. And if you graph those data pairs, x comma y, you end up with a scatter plot as a result. And so you can use the scatter plot to visualize the correlation. And when you graph it, you can actually get some kind of an idea as to whether a significant relationship exists. But what we need is we have to have a formal hypothesis test procedure to determine whether a statistically significant correlation actually exists, so that your eyes can fool you, your eyes can maybe see patterns that are not statistically significant. So we need an objective test here to be able to tell the difference. So to visualize this correlation, typically if we graph the x values on the horizontal axis and simultaneously graph the y values on the vertical axis, you might see a relationship that looks something like this. So we have the x-axis on the horizontal side and the y-axis on the vertical portion of the graph. These scattered data points may have some kind of relationship here. There might be a slight positive correlation, meaning if I drew a straight line through here, that you would have some kind of relationship that might look something like that, if it was a linear relationship. And so that might be a slight positive linear correlation. If the data points are more tightly bound to each other, where you see that there is a smaller variation around that linear relationship, this would be considered a strong positive linear correlation. It is linear because the best fit line, or the line that would, or the relationship that you would use to describe between the points, would be probably a straight line, and it would be a positive correlation because the slope of this is positive. And when the data points all lie exactly on that positively sloped straight line, that's considered a perfect positive linear correlation. A very similar type of relationship can be seen if we have a negative correlation. So a negative correlation would just be a general downward trend. As the x value increases, the y value is actually decreasing instead of increasing. So we get a general downward trend for the slope. So this would be a slight negative linear correlation, and when the data points are have a smaller variation around that linear relationship. So if I have a straight line that would look something like this, that looks like we've got a relatively strong negatively sloped linear relationship. That would be called a strong negative linear correlation. And when all the data points lie exactly on that straight line negative slope, that is called a perfect negative linear correlation. There are other kinds of correlations that can occur, though. They don't always have to be linear. In this course, we are going to calculate on tests of linear correlation to determine whether there's a straight line connection or not. But there's a possibility that you don't get any correlation at all. So if the x value and the y values are completely unrelated to each other, then you get this type of graph scatter plot where there is no correlation. There are other kinds. This graph here looks to be like it might not be linear. It might actually be a curved relationship, and a reasonable guess might be that this is some kind of parabola, some kind of quadratic relationship through the points. And so that would be a strong quadratic or parabolic correlation. And if we had data points that were scattered around some sort of sinusoidal variation, where we have data points that vary periodically in the x and y pairings, that would be a strong sinusoidal correlation. So in this course, again, we're going to be testing just the linear correlation parts, but the you can linearize any of these equations and actually try, you can convert most problems into a linear correlation problem, or there are other techniques that you can use to do other kinds of correlation tests. So the formal hypothesis test for linear correlation would look something like this. First, we need to talk about how do you measure correlation? How do you tell how well the x values match some kind of relationship with the y values? And we use something called a correlation coefficient to measure this relationship. It's a measurement of how well the data fits a particular kind of correlation. And so when we talk about linear correlation, we use, for the population correlation coefficient, this is actually something called a the coefficient of linear regression. We use symbol rho, which in Greek sounds like the letter R, and we use that because it comes from the word for regression, the linear fit, the process of minimizing the distance between the a calculated linear relationship and the actual data points that are on the graph. So if we have a population correlation coefficient symbol rho for a sample, that same calculated value is R, a coefficient called the correlation coefficient correlation of linear regression. And so if this number is close to 0, whether it's a population or a sample coefficient, if that number is close to 0, it means that the two data sets are uncorrelated. There is no relationship between them. So if we get a value that is close to 1, positive 1, that means a positively correlated set. And if we get a number that is close to negative 1, it means a negatively correlated set linearly. So we're looking for a positive linear slope or a negative linear slope. The point is, it's not 0. It's away from 0 if we have significant linear correlation. So when we construct the hypothesis test, it will always be, remember, the claim that has the equal sign in it. So that means no correlation exists or rho equals 0. So we use the claim is that the population correlation coefficient is 0, meaning there is no correlation between the variables at all. So the alternative then would have to be that there is a significant correlation, and that would be that that correlation coefficient is not 0. It is away from 0, either close to positive 1 or close to negative 1, but definitely away from 0. So we can find evidence of either a positive linear correlation or a negative linear correlation, depending on what the sign is on this calculated correlation coefficient value. Notice that in order to calculate the test statistic, the R value, the sample linear correlation coefficient, we need to draw the hypothesis test as normal. So the critical region would be the value of the test statistic that allows you to reject the null hypothesis, which gives you any value for the sample correlation coefficient R that would be away from 0. The maximum value of this number is 1. The minimum value is minus 1. So unlike the regular t distribution or z distribution, which extend infinitely to the right and to the left, the correlation coefficient has a maximum value of +1 and a minimum value of -1. Significance level is interpreted the exact same way as a normal hypothesis test. It's talking about the percentage of experiments that, if you repeated with the same sample size, would be allowed to disagree with your confidence interval or the claim by random chance. So when we draw our distribution, the only difference really between a regular hypothesis test and this is that the maximum value here, or sorry, minimum value here and maximum value here terminate on the axis at +1 and -1. So when we do our claim, sketch the claim that the bivariate set of data is uncorrelated, meaning rho equals 0, that would have to be the middle of the distribution. Anything close to an R value of our sample linear correlation coefficient calculation that is close to 0 or not significantly away from 0 would give us a result that we would not be able to reject the null hypothesis. But if we find an R correlation coefficient that is close to 1 or an R correlation coefficient which is close to -1, then there's going to be a rejection region on the right side and the left side for the linear correlation test. If we end up with numbers that are over in this region, that would allow us to establish that we have a positive linear correlation. And if we get numbers down over here, we would have a negative linear correlation. So we need to find the critical values that separate the two regions. And where you find the critical value is you find it on table 5 in your handout on the formula book for this course. So table 5, the critical values of the Pearson correlation coefficient are. Here is what that table looks like. You'll notice that we only give you, in this example, 2 significance levels, 5% and 1%. And n is literally the number of bivariate data points. So how many x and y values you have, how many data points, how many dots are on that scatter plot. And so the critical coefficients are given. You'll notice that in order to, with only 3 data points, you've got to have a really, really close, almost perfect linear correlation in order to see a significant value. But when you get into 20, the number that is actually going to give you a significant linear correlation for a 1% test is 0.561. So somewhere here. So if your value of your correlation coefficient that you calculate for your sample is higher than 0.561 or less than negative 0.561, it will allow you to reject the null hypothesis. So this test statistic, that's the only thing that's left, is how do we actually calculate this? Well, it turns out that it's going to use an equation that uses standard deviation calculations between the spread of all the x values and the spread of all the y values. So to calculate the value of the sample correlation coefficient R, we need to have some statistics. And the actual statistics we're going to use are the statistics that are common when we calculate standard deviation. So we're going to need to add up all of our x values, all of the squares of the x values. We'll also have to do all the y values and all the squares of the y values. And then there's one thing that's new, and that's this. We have to calculate the product of the x times the y values. And we end up putting it into this relatively ugly looking equation, but remember, these 5 numbers just go into the equation. So once we have the sum of the x values, we actually put that into this location and this location in the formula. Once we get the sum of the square x values, that only occurs once. And when we do sum of the y values occurs in 2 locations. And when we calculate sum of the y squareds, that only occurs once. And the product, sum of the x times the y values, goes here. So you put in those 5 numbers into your formula with your sample size n. You'll recognize the denominator square roots are formulas that come from the calculation for standard deviation of the individual sets themselves. So the standard deviation of the x variable set and the y variable set themselves. Okay, so once we have these 5 numbers, you just plug them in, you get one value for the correlation coefficient. If it is close to 1, you get a positive linear correlation. If it is close to -1, you get a significant negative correlation. If it's close to 0 or not significantly different from 0, then we can't reject the null hypothesis, which is the claim that the data is uncorrelated. So here's the summary of the formal hypothesis test procedure. You use the same 7 steps that you normally do in every hypothesis test. First step is to identify the claim. The claim in any linear correlation test will always be that no correlation exists, which means rho equals 0. Because that has an equal sign, that is going to have to be the null hypothesis. The alternative hypothesis is that linear correlation, population linear correlation coefficient is different from 0, either close to 1 or negative 1. And so that you would have a alternative hypothesis that a linear correlation does exist. You identify the significance level alpha. That is normal procedure. Usually you're told that in the question. The two most common are 1% and 5% linear correlation, significance levels for this linear correlation test. The test statistic, remember, is that R value, so it's an R test, so that you'll have to calculate that number. So you draw your distribution, and you find your critical region, and in order to test it, you test it with this giant looking equation where you put in the values of the sum of the x values, the sum of the y values, the sum of their squares, and the sum of the product. So to find the critical value that will separate the rejectable from the acceptable region, again, you find that on the Table 5, critical values of the population coefficient R. And then you make a decision. Basically, if your sample R value has a number that is bigger than or equal to any of these critical values, or the critical value that you have for your specific sample size, then you're going to have that your sample coefficient is bigger than the critical value, and therefore statistically significantly close to 1 or minus 1. So let's just look at an example. Let's say you had a set of 7 data points. So with a set of 7 data points, I've got 2 critical values for the correlation coefficient, 0.754 and 0.875. And that's at a 5% significance level and 1% significance level, respectively. So let's say we had a 5% significance level. I would use the value R critical of 0.754. If I find my sample correlation coefficient is bigger than 0.754, that's either bigger than positive 0.754 or less than negative 0.754, it will be significantly away from 0, and that will allow you to reject the null hypothesis. So if R lies in the critical region, you reject your null hypothesis of no correlation. If it doesn't lie in the critical region, meaning it's less than this value for the correlation coefficient, you can't reject the null hypothesis. The last step is you write your conclusion. Now remember, just like when we did the introduction to regular hypothesis tests, the actual conclusion depends on what the claim is. If the claim is there is a significant correlation, well, that's the alternative hypothesis. You can only ever support or not find enough evidence to support the alternative. If the claim is that these variables are uncorrelated, that is the null hypothesis. So you'll either be able to make a conclusion that you reject that statement, that there is no linear correlation, or you don't have enough evidence to reject that statement. So the phrasing of the conclusion, of course, is always dependent on the which of the claims is the null or alternative hypotheses.